We're very happy to have Michelle Manus here today, who will be telling us about going around in circles, periodic points in dynamics. And how are you able to ask you questions?
Hey, yeah, thanks. So I would love people to ask me questions however they like. So I am going to try to keep an eye on the chat. If you put something in the chat, hopefully I will see it. And if I don't, also just I'll try to have pauses. And if I pause, feel free to just unmute and ask something or call my attention to something in the chat. And I want to say I really would love to have questions. I have a lot of stuff in the talk, but I would be super happy to not get through the whole talk and just tell you stuff that you're more interested in because you're asking questions. So please, I not only welcome questions, I really actively want them. So please let me know if you've got any. Awesome. So let's get started then. I'm gonna just introduce kind of the basic objects that we're gonna talk about. And so the first thing that's important, right, if you look at my title, it's periodic points in dynamics. So I'm going to tell you what I mean by dynamics, first of all. So a dynamical system kind of fundamentally is just a function, right? I've got some set, it can be any set in the whole world, and I have a function from that set to itself. And the reason that it's important that the function sort of goes from my set to the same set is that then I can iterate. I can kind of take whatever output I get and put it back into the function as my next input, and then keep going. Take that output, put it back in, take that output, put it back in. So I have this exponent notation, f to the n, to mean this iteration, this composition of f with itself. So I do f with itself n times. So I take some sort of seed value alpha, and I do f of alpha, and then f of alpha, and then f of f of alpha, and so on. And again, okay, so that's dynamics. Periodic points, right? A point is periodic if when I do that some number of times, I get back to where I started, right? So you can kind of picture, I've got my point alpha, and it maps to f of alpha, and that maps to f of alpha, and so on, and it goes some number of times and eventually comes back to where I started. So that's why I'm thinking about kind of going around in circles, right? I'm going in this orbit around alpha. And one kind of quick thing to note is that I said it's periodic with period dividing n if the nth iterate brings me back to where I started. Because think about, for example, if alpha is just a fixed point, right? So I take alpha and I do the function f, and f of alpha and alpha are exactly the same. Well, then if I do f again, right, f squared of alpha also gets me back, and f cubed also gets me back. Any number of times gets me back. And if alpha is, let's say, on a 2 cycle, right, if I have alpha goes to f of alpha and back again, right? So I'm kind of hopping back and forth. Well, then if I do it 4 times, I go 1, 2, 3, 4, I'm also back. And if I do it 6 times, 1, 2, 3, 4, 5, 6, I'm also back, right? So I have to be a little bit careful. Alpha can be any point with period dividing n, and it'll be kind of a solution to this equation. Okay, so
by the way,
yeah.
So I have a few questions. One,
sure.
By dynamical systems, you mean like just the S combined with that map F from S?
Yeah, it's a set with a self map. Yep, that's all it is. So this is what's called a discrete dynamical system. Yeah.
And basically, a point alpha, its period is n if n is the first positive.
Exactly. Right. Exactly right. Yeah.
So
thanks for that clarification.
Above case, its period is exactly 2.
Right. So here we would have period 2. Here we would have period n, and I had the fixed point before, which would have period 1. So usually we want to know kind of what's the smallest period, the exact period. But this shows us that we have to be a little careful when we ask that question. Good point. Yeah. All right, so the last thing to talk about is a field. So I think some of you maybe have studied a little bit of abstract algebra and might know what a field is. And if you don't, that's okay, because all you really need to know, a field is a number system where I can add, subtract, multiply, and divide, except of course I can never divide by 0. That's bad no matter where I live, right? And there are lots of fields that you already know about. So for example, the rational numbers. Everybody knows and loves the rational numbers. So we've just got a over b, where a and b are integers. Of course, b can't be 0. And I have this kind of equivalence relation. I know what it means for two fractions to be equal, right? Like a half equals 2/4. Yeah, Anuj raised a hand.
I thought like a field have like the associative property, right?
Yeah, so I'm being absolutely. I'm being very vague here. I'm not giving you the full axiomatic definition. That's exactly right. So if you've seen that, that's great. But I mean, this essentially means addition, subtraction, multiplication, and division work the way that you're used to, right? So meaning that you have the associative property, that multiplication distributes over addition, that I have a 0 that acts like an additive identity and a 1 that acts like a multiplicative identity. So there's lots of axioms, but this is kind of my shorthand for folks who haven't seen it before. But you're exactly right. It's a bit more complicated than that. Okay, so we know the rational numbers. We all also know the real numbers, right? And the real numbers, I will say, a little harder to define very rigorously. It's very cool if you take a real analysis class and learn how to do that. But for right now, you can just think about the number line, right? So here's the real numbers. I've got 0, and I've got sort of positive numbers to the right and negative numbers to the left. And I can sort of tell you where a number is. And I've got like pi over here. And I've got, you know, minus square root of 2 over here, and all those fun numbers, okay? So we've got the rational numbers, we've got the real numbers. We've also got, yeah?
All those definitions, all those more rigorous definitions really make you appreciate the numbers that you took for granted.
Yeah, exactly. All right, and now we've got the complex numbers. So some of you may have seen the picture of the complex numbers. So I have a plus bi, where a and b are real numbers. So that's why I have kind of two copies of the real line here. I've got the real part and the imaginary part. And if I just plop down a number right here, a plus bi, right? So this is kind of a, and this is bi right here, and that gives me a complex number. So one thing to kind of keep in mind is that the real line, right, sits inside of this complex plane. It's the numbers where the imaginary part is 0. So that's just a thing to remind yourself of later, because I'm going to ask you to kind of make some guesses. Finally, some of you I know have thought about modular arithmetic, like clock arithmetic, working like mod 7 or mod 5. And it turns out if you work mod a prime, then what you actually have is a field. That world, you can add, subtract, multiply, and divide, except of course you can't divide by 0. So these are fields that you may be more or less familiar with, but there are lots of other fields in the world. So we have, for example, if I start with the rational numbers and I say, yeah, the rational numbers are cool, but I really care about the square root of 2, I can make this what's called a finite extension. So this says I throw in that square root of 2, and then I kind of close it up so that I'm allowed to add, subtract, multiply, and divide everything in there, right? So I need like a 1 over square root of 2 and a minus square root of 2, and I need like a plus b root 2 for all the a's and b's. So I get this kind of finite extension where I've kind of added one new element. And I can do this for lots and lots of examples. These are called number fields. I also can do function fields. So here, K is any of those fields I already talked about. Anuj, I'll get to you in 1 second. Let me just finish this sentence. So all those fields I talked about, the rationals, the reals, the complex numbers, and I can take polynomials, ratios of them, something like this, x squared plus 1 over 2x. There's a rational function. And if I think about this world, where the coefficients come from a field, I also get a field there. Okay, Anuj, what was your question?
Is it really a finite extension if like you're adding like root 2, 2 root 2, 3 root 2, and so on? Like, is it really a finite extension?
Yeah. So it kind of seems like I'm adding infinitely many things, but in fact, I'm really not. So this notion of finite, if you've thought about vector spaces at all, it's really that kind of notion of a finite dimension, right? I really have, it looks like this. It looks like a plus b square root of 2, where a and b are rational numbers. And it turns out this is enough to get me I can get all the reciprocals and everything that way too. So it's a kind of two-dimensional space, right? I have these two parameters.
Mm-hmm. Like, for example, 1 over the square root of 2 is the same as the square root of 2 over 2. So
exactly right. So see how you can put it in that form. Exactly right. Yep. And finally, you may or may not have heard about these things called p-adic fields. If we have time, I'll tell you a little bit about them at the end, because I think it's a really cool kind of coda to this talk, because what I'm going to tell you about, we have no idea really what happens in these p-adic fields. And they are ones that number theorists like me care a lot about. So, and if I don't have time, if we run out of time, then that's a thing for you to go explore, because they're super cool. All right. So, so where are we? So we have a field, right? One of these worlds where I can add, subtract, multiply, and divide. I have a polynomial whose coefficients come from that field. And I know what it means to be periodic. I know that it means that I iterate the function some number of times, starting from alpha, and I come back to where I started. And if I think about this, I can turn it like a little more algebraic. What I can say is that point alpha, right? It's a number, it lives in my field. So it's a solution to an equation, or I can even think about it as a root of a polynomial, right? So if, like, for example, if f, oops, I've been using z, let me keep using z. If f is z squared plus 1, right, then like the third iterate of f is z squared plus 1, and then I square that and I do plus 1, and then I square that and I do plus 1. And if I expand that whole thing out, I just get a big high degree polynomial, right? It's still a polynomial. So one way to think about periodic points is they're roots of polynomials. And that's a really convenient way, because we know a lot about polynomials. We study them like starting from very early in school. All right, so here's our big question. I have all these fields that I know about, and I have polynomials, maybe with coefficients in that field. And I want to ask the question, do I have a periodic point of sort of a fixed period? And like Dallas said, right, that when I say a point of period n, I really mean smallest period. I really mean that first time I come back, right? So do I have a point of period n that lives in that field? And it turns out the answer really depends on what field I'm asking about. So I'm going to go through and tell you kind of what we know for some different values of k, some different fields that we're friends with. All right, so let me pause. Does everybody kind of get the question that we're asking? So I've got a polynomial that lives in some field, and I want to know, do I have a point of period n in that field? Do I have a 4 cycle in that field? Do I have a 1 billion cycle in that field? Do I have a fixed point in that field? Okay, so the first one that we can answer is for the complex numbers. So there's this very cool theorem that we know about the complex numbers. It's called the fundamental theorem of algebra that tells you how important it is. And every polynomial with complex coefficients has a root in the complex numbers. So if I think about these fixed point polynomials, right? Every single one of those has a root in the complex numbers. Okay, so you might think, well, okay, a polynomial with complex coefficients, it's got to have points of every possible period, because the periodic points are roots of those polynomials, and all of those polynomials have roots. And so, right, it just seems to make sense. But it turns out that's false, because we remember what I said on that first slide, that we have to be a little bit careful about what we mean by period n versus period dividing n. Yeah, question.
But how about like x squared? Oh, never mind. I take it back.
Oh, okay. All right. Let me know if you have a question. All right. So I'm going to give you an example to see how this can happen. So here's a polynomial, pretty straightforward, z squared minus 3/4, right? The fixed points of that polynomial, they're roots of f of z minus z, right? So if I do z squared minus z minus 3/4, and I factor it out, here's what I get. So can somebody tell me what fixed points I have for this polynomial?
3/2 and minus 1/2.
Yeah, so this factor here gives me z equals 3/2, and this factor here gives me z equals minus 1/2. And we can check, right? Plug these in. If I plug in 3/2, okay, I get 9/4. 9/4 minus 3/4 is 6/4, and that gets me back to 3/2. And if I plug in minus 1/2, minus 1/2 squared is 1/4. 1/4 minus 3/4 is minus 1/2, right? So those really are genuinely fixed points. All right. Points of period 2 are roots of this equation, right? So I did the algebra out for you. I did f of z, and then I did f squared of z, right? That's f of z squared minus 3/4. And what do you notice? What are my points of period 2 for this function?
They're the exact same ones as before.
They're the exact same, right? Look at my roots here and look at my roots here. I get 3/2 and minus 1/2 again. So I don't actually have a real genuine point of period 2. I only have fixed points that are kind of in disguise, masquerading as points of period 2. Anish, did you have another question? Or is your hand just still up from before?
Still up from before.
Oh, okay. All right. Just making sure. All right. So this can happen, right? We can sort of be tricked. This is why we have to be a little bit careful. So, right, these polynomials have the same roots, so there are no points for this polynomial of exact period 2. But it turns out that's basically the only thing that can go wrong for the complex numbers. So there's this theorem from I.N. Baker from 1964. So he proved, so if you don't know what a field of characteristic 0 is, don't worry. Everything we talked about almost, so the rational numbers, complex numbers, real numbers, those all are. And this k bar, what that means is that every polynomial has roots. So for the complex numbers, they are a field of characteristic 0, and in that case, k and k bar are just the same. So we can rewrite this to say, let f be a rational function over the complex numbers. If it has no points of exact period n in the complex numbers, then the sort of pair of the period and the degree can only be one of these options. And if it's a polynomial, the only thing that can happen, right? This says I have a period 2 point and a degree 2 polynomial. So a quadratic polynomial can be missing period 2 points, but nothing else can ever go wrong. So I basically showed you the only bad thing that can happen in the complex numbers. So if I hand you a polynomial with complex coefficients and I say, does it have a point of period 572? You can say yes, right? Does it have a point of period 4? You can say yes. Does it have a fixed point? Yes. Does it have a point of period 2? Well, if it's a quadratic polynomial, you'll have to check, but otherwise, yes. Right? So it almost never goes wrong. Yeah.
So by the way, does k bar mean like the algebraic closure?
Algebraic closure. Yep, exactly right. Yeah, so this is the algebraic closure. So for the complex, right, they are already algebraically closed. So that's not different. Okay. So we have a pretty complete story for the complex numbers. We know exactly what can go on, and it's not very complicated, right? The answer is basically, for almost always, the answer is yes, I have points of that given period, with maybe one exception that I have to be a little careful about. What about the rational numbers or a number field? So the setup is exactly the same. And here's a really cool theorem. So notice this is that theorem we just saw was from 1964. This is from 1950, so not that far apart in time. And Northcott proved that a rational function, so again, remember this means kind of polynomial over polynomial. It's just a more general case, but this is also true for polynomials themselves, which are what we're talking about. If I hand you a polynomial with, say, rational coefficients, and I say, how many periodic points does it have in the rational numbers? The answer is always finitely many, right? So compare that to the complex numbers. The complex numbers, you had points of every possible period. So you certainly had infinitely many periodic points, because I could have, points of period 1, 2, 3, 4, 5, etc. forever. So I have infinitely many periodic points. This says I have finitely many altogether. So that means, after, say, period 5, there's no more periodic points of higher period or something like that. Now, the thing to be careful of is finitely many can still be really big, right? There are big giant numbers that are still finite. But it does mean that for every single polynomial in the world over the rational numbers, there's only finitely many sort of cycle lengths, and then you're done. And there's this very hard conjecture. Yeah, go ahead.
So basically you're saying it only has finitely many periodic points inside the rational numbers.
Inside the rationals,
maybe
exactly.
The complex numbers.
Yeah, and definitely, right? Because the rationals sit inside the complex numbers. So if I just turn my head and think about it as a polynomial with complex coefficients, it for sure has infinitely many there. But if I'm asking about sort of inside the rational numbers, only finitely many. So this, what's called this uniform boundedness conjecture, this is a really powerful and really hard problem. And it says that there's a constant that depends on the degree. So for example, if I fix polynomials of degree 5, there's some constant, I don't know, maybe 30. And no polynomial of degree 5 has more than 30 periodic points in the rational numbers. Okay, I totally made up the number 30. Nobody even has a guess for degree 5. But for degree 2, for example, we have a guess that the maximum number is 9. That if I hand you any degree 2 polynomial that has rational numbers as coefficients, and you find all of the periodic points that live in the rational numbers, we think there are not more than 9 of them. That's a really small number, right? That's teeny compared to infinitely many. So why is this so much harder than what Northcott proved? If you think about what Northcott proved, it is possible with Northcott's theorem that I could have like a bunch of cubic polynomials where the first one had 2 periodic points, and the next one had 4, and the next one had 8, and the next one had 16, and the next one had 32, right? Each individual one has finitely many, but if I look at the whole family, each one has more and more and more and more and more of them. So it's kind of unbounded, right? It can get as big as I want. Could I find one with more than 1 billion? Yeah. Could I find one with more than a Google? Yeah, right? Because I just go far enough out. So this says that that's impossible, that if I know the degree, I know an absolute maximum number. Okay, so I want to tell you at least a little bit about how we know that this is true, this Northcott's theorem. And this uses some cool technology that are called heights. So I'm going to define it for the rational numbers. I'll say, again, if you've taken a little abstract algebra and you know about number fields, you can do a slightly more complicated definition that works there. But this is a sort of a straightforward one to use for the talk. So if I have a rational number a over b, I define the height to just be the maximum of the absolute value of the numerator and the denominator, right? So for example, like the height of minus 10 over 19 would be what?
It'd be 20 net. It'd be 20. Wait.
It would be
19?
19,
Oh,
right?
maximum.
Yeah, 19, because it's just the bigger, right? I just take the bigger absolute value of negative 10, absolute value of 19, the bigger one's 19.
What if it's an
Oh, and there's
unsimplified
the-
fraction?
Yeah, right. You do want it to be in lowest terms, yes, right? Otherwise, it's not well defined. So you have to make sure that A and B, right? I should have probably said that this is like with GCD equal to 1. You do have to write it in lowest terms because you want there to be kind of a unique answer. Okay, oh, somebody put in the chat how many upper bounds for the number of fixed points are known. So, I mean, I think, so if I hand you a particular polynomial, it's not hard to decide if it has, let me think about that. Is it hard to decide? I think it's not hard to decide if it has a fixed point in the rational numbers. But if you're asking about sort of upper bounds for the number of periodic points, it's like really unknown. We have guesses for quadratic polynomials over the rational numbers, right? That's what I said, we guessed that there's 9. We have guesses for cubic polynomials over the rational numbers. We have guesses for quadratic polynomials over kind of degree 2 extensions. And I forget their guess. I think it's maybe 16 or 17, but that could be wrong. But we don't actually, like we don't actually know any answers to any of them. Yeah, question.
Oh, when you say guess, like what do we need to do to verify this guess?
Yeah, well, we would need a rigorous proof, right? So when I say guess, what I mean is people either have like computed lots of examples. Well, they've certainly computed lots of examples. And then they have some kind of reasoning for thinking that that's true. So here, let me tell you for the quadratic polynomials, what we can prove, if a quadratic polynomial doesn't have a period bigger than 3, no cycle bigger than 3 that lives in the rational numbers, then it definitely has 9 or fewer periodic points. Because we can completely say what will happen for fixed points, 2 cycles, and 3 cycles. We can completely understand it. But what we can't prove, and I will say, we know for certain, no polynomial with rational coefficients has a 4 cycle in the rational numbers. It also doesn't have a 5 cycle in the rational numbers. But we cannot say for certain, for example, that there's no 10 cycle in the rational numbers. We just don't know. The math is too hard to actually prove that for sure. So what we can say is, if it's true, we think it's true, if it's true that there's no sort of really long periods of rational numbers, then 9 is the right answer. But that's a big if that we don't know how to prove. Yeah, okay, so so let me come back to heights. So we've got the idea of heights. So here's the really cool property of heights. So if I give you like an absolute value, right? If I say list all the rational numbers with absolute value less than 1, like you can never finish, right? Because you'd be like a half, a third, a fourth, a tenth, 1 over 100. Like there's infinitely many of them. But it turns out that sets with bounded height are always finite. So let's just see that in action. So you can either shout out or put in the chat, what rational numbers would have height less than 4? Can anyone tell me? So I see a half, I see a third. And I'll point out that anything I can say, I can also make the negative of because
0?
I'm taking absolute values. 0, everybody forget 0, thank you. 0, and negatives, right? Plus, and I saw 1, so I'm gonna do plus or minus 1. And I saw, right, we can do the reciprocals. So we can do 3 and 2/3. Oh, we got 2/3. What else do I have? Plus or minus 2. Am
3
I
halves?
missing?
1.5.
3 halves, thank you. Yeah, plus or minus 3 halves. Is that all of them? I've got the answer on the next
so.
page. You think so? Let's check. Here we go. So yeah, 0, plus or minus 1, 2, and 3, plus or minus a half, 3/2, 1/3, and 2/3. Okay, so heights are really cool because they let us like actually understand what happens to these periodic points. Is this like fairy? Oh, you know, fairy sequences are so cool. Is this? That's an excellent question. I have not thought about that connection to fairy sequences. I would have to think more about the connection of heights to fairy sequences because I know them sort of from a different angle. But all right, so but the sort of the key thing to think about, right, is if I have a polynomial, like let's say I have f of z is like, I don't know, 5z to the 10th plus 4z to the 7th minus a half z cubed plus 2. And I plug in some number alpha, right? So f of alpha is 5 alpha to the 10th plus that other stuff. And I ask you about the height of f of alpha compared to the height of alpha. Well, like, right, this term, right, the way that I've defined it, the height, if I'm just dealing with rational numbers, the height is like a positive integer, right? So if I raise it to a big power, if I raise alpha to a big power, kind of the height of f of alpha should be about the height of alpha raised to the 10th power, but that's not going to be exact because I have all this other nonsense going on, sort of adding and subtracting that might change things a little bit, right? But sort of approximately, that's what this little squiggle means. Approximately the height of f of alpha, right? This term, this lead term of the 10th power should kind of dominate. It should be the one that's the most important. And in fact, we can make that really precise. There's a constant, so this little c sub f says it depends on the polynomial. It depends on the coefficients of the polynomial. That constant might be really big, it might be really small, but if you hand me a polynomial f, I can figure out that constant, and then I can say that the height of f of alpha looks like the height of alpha to the dth power, except it's bigger than the height of alpha to the dth power, kind of up to this constant multiple, right? So I can kind of compare them really precisely. And why is that important? Well, let's go through this. Okay, so I know that the height of f of alpha looks like the height of alpha to the d times some constant. So let's apply that to f squared of alpha. Well, f squared of alpha, right? This is f of alpha. So I'm going to say that this looks like c times the height of f of alpha to the dth power, right? I'm sort of applying this equation with f of alpha in the role of alpha and f squared of alpha in the role of f of alpha, right? And then I apply it again and I get another inequality, right? Because this inside here, maybe I'll write it out. This is bigger equal to c times h of alpha to the dth power, right? So I raise all of that to the d, and that's how I get this sort of next equation. Okay, so I can kind of use this inequality and I can say, okay, the height of f squared of alpha is bigger or equal to the height of alpha to the d squared power times some constant. The height of f cubed of alpha, if I just do that game again, is some bigger or equal to some constant times the height of alpha. And I can keep going, and I get at the nth stage, the height of f to the n of alpha is bigger or equal to some constant times the height of alpha to a power, right? And right, this is a very specific constant and a very specific power. Now, what's the key thing? Suppose alpha is a periodic point, right? So then f to the n of alpha, this is really just alpha if alpha is a periodic point, right? So those are the same, height of alpha on this side and height of alpha on this side. And I just do a little bit of algebra and I can see that the height of alpha is less than some constant. And what did we say? We said sets of bounded height, right? Imagine that constant is 4. If that constant is 4, then we listed all the possibilities for what alpha might be, and we could just test them all. And even if that constant is big, that constant could be a billion, but we could still systematically list every rational number with height up to a billion, right? It would be plus or minus, all the integers, and then plus or minus 1 over all the integers, and so on and so on. And so it's a set of bounded height, so it's finite. So that's kind of how Northcott proved his result. So, okay, so I'm just going to point out, this is really different behavior, right? We have an answer for the complex numbers, and we have an answer for the rational numbers, and they are just wildly different from each other. So I have a question for you. So remember our picture, okay? We've got the complex plane, right? So this is the complex plane. The real numbers, right? They live inside of here, but they're very small. They're right there. And the rational numbers, right? They kind of live inside the real numbers along this line. They're densely populated along there. Like near any real number, I've always got rational numbers. So do you have a guess what might happen for the real numbers? So I'm asking the same question. If I hand you a period, will I have I have a polynomial with real coefficients, and I say, do I have a point of period 5? Do I have a point of period 300? Do you have any guesses what my answer might be?
Indeterminate.
So, yeah, and so I see an indeterminate and another indeterminate that you kind of can't know. Yeah, I mean, it turns out in a sense, you're right. It kind of, lots of different things can happen, but we can completely classify what those things are. So let me give you a couple of examples first, and then I'm going to give you sort of my favorite theorem in all of math. I think it's just really the coolest theorem. Okay, so my first example is this one. I take the polynomial z squared plus 1. So fixed points would be roots of z squared minus z plus 1. And you can, if you want, hit that with the quadratic formula and convince yourself that there are no real roots. The roots of this guy are complex numbers. So this has no fixed points in the reals. And it turns out that it has no periodic points in the reals at all. 0, none. On the other hand, this polynomial, not much more complicated, z squared minus 29 over 16, I gave you a 3 cycle. So minus a fourth goes to minus 7/4. I can check that, right? Minus a fourth squared is 1 over 16. So that gives me minus 28 over 16, which reduces to minus 7/4. Minus 7/4 goes to 5/4. And if I plug in 5/4, I get back to minus a fourth, right? So I really have a 3 cycle here. And it turns out not only do I have a 3 cycle, but I have points of every possible period. So if I hand you a number, 527, and I say, does it have a point of period exactly 527? The answer is yes. All right, and how do I know that? It's very important that I picked one with no fixed point, and I picked one that I knew had a 3 cycle. So I'm going to tell you the coolest theorem ever. This is called Sharkovsky's theorem. And in order to do that, I have to give you a weird ordering. Oh, there's a question. Would the reason be, the reason be that no periodic points be for the first one, that absolute value of z is less than absolute z squared plus 1. So if I picture, so one way to see it for this guy, I see what you're saying, is if I plot sort of z squared plus 1, right, there's a plot of my function. And if I draw the line like y equals x, those are never going to intersect, right? Because the parabola always sits above. Yeah, so that for this function, there's a way to see that I'll never have them. And as I iterate, right, it's gonna kind of get even more positive. Okay, so I'm gonna tell you the Sharkovsky ordering of the natural numbers. So here it is. Okay, 3 is bigger than 5, is bigger than 7, is bigger than 9, et cetera, et cetera. So all the odd numbers. 3 is the biggest odd number, and they kind of go in what we usually think of as increasing order. Every odd number is bigger than 6, which is bigger than 10, bigger than 14, bigger than 18. And again, here's 2 times the odd numbers in what we usually think of as increasing order. And then we have everything that's twice an odd number is bigger than 12, which is bigger than 20, bigger than 28, et cetera. And I keep going, and everything with an odd factor is bigger than every just pure power of 2, right? And I've got 2 to the n, 2 to the n minus 1, et cetera. And then 4, 2, and 1 is my smallest natural number. Okay, so here's the kind of factored form of that ordering. So all the odd numbers on top, 3 is the biggest, and then 2 times an odd number, 4 times an odd number, 8 times an odd number, et cetera. And finally, powers of 2 decreasing. Okay, so I have this very strange ordering on the natural numbers. And here's my theorem. Okay, so I have a continuous function. So polynomials are continuous functions, but this is like much more general, right? Just any function I can draw without looking at my pencil. The sine function, the cosine function, sort of any nice kind of smooth thing that I can draw. Suppose it has a real point of exact period n, and that n is bigger than k in the Sharkovsky ordering, then it also has a real point of exact period k, right? So let's go back to this ordering. If I have a real point of exact period 18, then I definitely have points of all of these other periods below 18. And in particular, right, this theorem is sometimes called period 3 implies chaos. If I have a real point of period 3, since 3 is the biggest number, I have points of every possible period. If I don't have a fixed point, I can't possibly have any other periodic point, because if I did, I would have a fixed point by this theorem, right? So I think that this is just like an incredible statement. And I'll just point out that there is also a converse. I'm not going to talk about the converse because it's not really about polynomials, but I can cook it. If you hand me a number m, like you hand me 67, I can cook up a function that has a real point of exact period 67. And for everything bigger, it has no point of that period, but it, by the theorem, has points of every smaller period. Oh, can I explain the part about after the ordering? Yeah, so what the theorem says, let me just go to the ordering and tell you what the theorem says in words. The theorem says if I have a continuous function, and if I know I have a real point of period, let's say this is 20. I know I have a real point of period 20, then I definitely have points of every other period in the real numbers. So in particular, if I have a point of period 3, I have a point of every order of every period. And if I don't have a fixed point, I don't have points of any other period as well.
If you have a point of some period, then you also have a point of every smaller.
Exactly. Smaller in this weird, funny ordering, right? So for example, I can sometimes have finitely many, because I could cook it up so that I have points of period 4, 2, and 1 and nothing else. I sometimes have infinitely many, but I'm also missing infinitely many, because I could, for example, decide that I have points of period, what is this, 40, and everything below 40, but nothing above 40, and both of those are infinite sets. And I can sometimes have points where I only miss finitely many. Like I could have a function that only has period 9 and smaller, but not 3, 5, or 7. And I could have ones where it's everything, as long as I have a 3 cycle. And so what's really incredible is this theorem only uses kind of ideas from calculus to prove it. So I'm going to talk you through how the proof goes, because it's just really, really striking to me. So there are kind of 2 big ideas in the proof, and you just use these 2 big ideas over and over. So the first idea is, okay, so I have this interval I on the x-axis, and suppose when I plug I into my function, right? So here's a graph of my function. The blue is the graph of my function, and the yellow is the line y equals x. If when I plug I plug I, that interval, I plug all those points in to my function, I'm going to get some y values out. And if those y values, imagine kind of rotating this y-axis down, this f of y that's marked on the y-axis kind of, f of I. Maybe let me do that actually. And f of I sort of covers I. If that happens, then I definitely have a fixed point in that interval. And the reason is just the intermediate value theorem. So kind of here's the kind of formalism of it, but I think the picture is pretty convincing, right? You just draw the picture and you see it happening. But the intermediate value theorem says, okay, well, since the y values that I get contain this interval I, something must map to the left endpoint, right? And that something sits between A and B. So in other words, I have some C1 where f of C1 minus C1 is less or equal to 0. Similarly, something in there must map to the right endpoint B, right? So I have some C2 where f of C2 minus C2 is bigger or equal to 0. And then the intermediate value theorem basically says that somewhere between C1 and C2, something gives is a root, right, of f of w minus w equals 0. So, and that's exactly what it means to be a fixed point, right? So the first observation just says, if the image of my interval kind of covers my interval, then somewhere inside I have a fixed point. First observation. Second observation says, if I have the interval I, and I have the kind of associated y values j, and if j, if f of I covers j, right? So let me sort of mark where f of I is here. I'll highlight it. So here's f of I, those y values, and j is kind of inside of that. Then I can just shrink I down so that it's an exact match, right? So in other words, if the y values of I sort of more than cover j, I can just shrink I down a little bit so that it exactly covers j, so that I get it on the nose. Those are my 2 observations. So let me try to kind of give you at least a little bit of the flavor of how these 2 observations let you prove the theorem. So the first thing is, if I have any k cycle at all, then I have a fixed point. How does that work? So notice that this doesn't say that x1 maps to x2 maps to x3. All I've done is I've put the points kind of in increasing order on the real line, but it could map like x1 goes to x3 goes to x2, right? They could map all over the place. But the point is, whatever x1 is, it's the smallest. It maps to one of the other ones. So f of x1 is bigger than x1. Whatever xk is, it's the biggest. It has to map to one of the other ones because it's a cycle. So f of xk is less than xk. And now I just use the intermediate value theorem. Since f of x1 minus x1 is negative, and f of xk minus xk is positive, somewhere in between, I must have f of x minus x is 0. And that's a fixed point for my function. So somewhere in the middle, right, in between x1 and xk, I have a fixed point. All right, that's, I mean, isn't that, I mean, we just proved like a really cool theorem using just the intermediate value theorem. I think this is really amazing. All right, let me see, how's my time? Why do we need the Sharkovsky ordering? So I will say all I did, I only proved one thing. All I proved was that if I have a bigger period, I definitely have a fixed point. But there's other things to prove, right? Like if I have an odd, if I have period 3, I have every possible period. If I have an odd period, I have 2 times an odd period, right? It's sort of, there's a lot more structure in the Sharkovsky ordering. But almost all the proofs are similar to what we just did with just a little bit more bookkeeping. So let me show you, I'm actually gonna, I'm gonna skip to, well, let me skip to the period 3 implies everything. And maybe that will, I'm skipping a little bit. Sorry if this makes you a little seasick, but let me show you how we're using the Sharkovsky ordering here. So period 3 implies every period. So we're going to assume we have a 3 cycle, right? So A maps to B, maps to C, maps back to A. And I'm setting it up so that A is definitely the smallest one, right? I can just rename them otherwise. So I'm starting with my smallest one. Either I go from the smallest to the middle to the biggest and back, or I go from the smallest to the biggest to the middle and back, right? That's what these 2 cases say. So A is, I'm sort of saying, pick out the smallest one. It either maps to the middle one or the biggest one. And the 2 cases, you kind of have to deal with them separately, but they look really similar. So I'm just going to do the first one. So suppose it maps from the smallest point to the middle point to the biggest point and back again. And I'm going to prove I get every other possible period, right? Okay, so here's my intervals. I have this interval I0, which goes from A to B, whoops. And I have this interval I1, which goes from B to C. And since A maps to B and B maps to C, right? F of this interval looks like this red curve here. It covers the second interval. And since B maps to C and C maps back to A, right? F of this second interval of I1 covers the whole thing, right? So this is kind of the picture to have in your head. And so what I want to do, I want to find a point of every period n for n bigger than 3. Notice I'll have to kind of special case period 2. Period 1 I've already taken care of, because I said if I have any cycle at all, I have a fixed point. So I would have to treat period 2 a little bit separately. But this will get me every point bigger than 3. And the way I'm going to do it is just use that second observation a whole bunch of times, right? That observation that says, if the image of an interval covers another interval, I can shrink it down to make it exact. Okay. So here we go. All right, so the image of I1, right? It covers the whole interval. So in particular, it covers I1. So I'm going to shrink it down to make it exact. I'm going to take A1 to be the subinterval so that A1 exactly maps onto I1. Okay, and then I'm going to do it again. A1 exactly maps onto I1, but that covers A1. So I'm going to shrink it down to make it exact. I'm going to find A2. So now what I have is A2 exactly maps onto A1. A1 exactly maps onto I1. And I'm going to just keep going. Smaller and smaller and smaller intervals where each time I get this exact mapping that I want. So an minus 2 maps exactly onto an minus 1, etc. Up to A2 maps exactly onto A1, maps exactly onto I1. Okay? I see there's a couple questions. So let me just finish this thought and then I'll come look at the questions. All right. So now I use the fact that I0 covers I1. So in particular, I0 covers this little tiny interval an minus 2. So again, shrink it down to make it exact. Take this little subinterval an minus 1. This guy exactly covers an minus 2, exactly covers an minus 3 all the way up, exactly covers I1. Okay. All right, we're almost there. So now we've got we've got I1, right? It covers that whole interval from I0 and I1. So I can take a little subinterval that exactly covers this an minus 1. So now I've got what I need. I've got this tiny subinterval that covers this. And when I do it n times, I exactly cover I1. So now if you think about it, what I have is this little subinterval covers itself after n iterates. And that means there's a fixed point inside there after n iterates. But a fixed point after n iterates means a point of period n, right? So let me skip. So here, this is kind of what I just said, right? If I take this little tiny interval, right? I do f squared, f cubed, etc. And after n times, I cover itself up again. And then that tells me there's a fixed point inside this interval. But a fixed point for fn, right? Remember, I have to be a little careful because a fixed point for fn, right? That's a root of, well, it's a solution that looks like this, right? Fn of alpha equals alpha. It might have period dividing alpha, but in fact, I cooked it up so that's not possible because I only land over on this spot every n times, right? I start here and I go to the left interval and then I stay in the right interval the whole time. And I'm only over here every n times. So it has to actually be a genuine period n and not something sort of smaller masquerading as period n. Okay, so I'm gonna pause and check because I saw that there were a couple of questions in the chat. How does the second picture cover everything in the previous slide? Oh no, I should have been where I was. Sriyam, can you tell me what your question was about? Because I don't know which slide I was on that. Or...
Like when you're at A, B, and C, A less than B less than C.
A less than B less than C. That was back here. Yeah. Okay.
How did you get the second one?
This second picture down here?
Yeah.
Yeah. Okay. So I'm looking at this interval, right? So since B maps to C, here's where f of B is. I'm kind of, imagine I'm taking the graph and I'm tilting it horizontally so that it's, instead of sort of an XY, it's like laying along the x-axis so I can kind of superimpose the intervals. So f of B is equal to C. F of C is equal to A, but because it's continuous, the function has to be nice and smooth in between there. Right, so if I sort of, maybe if I try to do it in 2 dimensions, it's a little clearer. So here's, let's say A, B, and C, and here's, actually, let me make this a little neater. Okay, so here's, let's say A, B, and C, and A, B, and C, right? F of B equals C, that's up here. F of C equals A, that's down here. And I know the function is nice and smooth, so I know it does something like this. Right, that's the picture. Or it could like go up and back down, but in any case, right, the Y values cover all of this interval right here. Does that help?
Yeah, thank you.
Yeah, okay, good. Awesome. Okay, so so I'm not gonna get to chaotic numbers, but that's because you all asked excellent questions. So I'm gonna stop. I'll say that there's lots and lots of other cases to kind of finish the proof of Sharkovsky's theorem, but this gives you the flavor that it's all very similar to this. And I just want to end with telling you why I think this is kind of the coolest theorem, like what I love about this. Oh, I see that there's a question. Let me get to that last question at the end, but I want to tell you why I love this theorem so much. So first of all, it's got a really simple hypothesis, right? I have a continuous function. That's like that's so broad. That's so many functions, all like it could be so many things. And it's got this incredibly powerful conclusion about the existence of periodic points. And then the proof is really kind of understandable. It's really kind of keeping track of things and the intermediate value theorem over and over again, and just kind of some careful thinking. But then I feel like there's also this little bit of magic of like, where did this ordering come from? How did Sharkovsky know? Like, it's much more than just period 3 implies chaos, right? That it's like this whole ordering, and how did he like come up with that in the first place is completely, I feel like he must have just thought so hard and worked so hard and had this incredible insight. And it feels almost like magic to me that you would sort of be able to see that and sort of know that that's true. Like the proof I can make sense of, but how did he come up with it? It feels just like magic to me. So this is why this is kind of miraculous to me. Okay, so there's a couple of questions. So the theorem still hold. So we're using continuity a lot of places in the theorem, right? We're using the intermediate value theorem, but like knowing that the image of the interval covers the interval, we're really strongly using continuity there, right? Like all these pictures, where did I go? Right, like this picture to argue that the image of one interval covers the other interval, we're really strongly using continuity in all of those. So it really does need to be a continuous function. But I mean, that's not a very big hypothesis. Would isomorphic fields have similar periodic? Yeah, if the fields are isomorphic, they're going to have the same, right? All the sort of dynamical behavior is going to be the same for isomorphic fields. Any other questions?
Well, I want to mention that other thing was something about isomorphic fields. Isomorphic means like they're just basically the same. You're just relabeling the elements.
You're exactly right. You're just relabeling things. So all the dynamics will be exactly the same with just new labeling. That's right. Anything else? All right. Thank you, everybody. It was great talking to you. I'm happy to sort of hang out and chat. Maybe I'll close my screen share so that I can see you better. But if anyone has any questions, I'm happy to chill here for a little bit and see. But I really enjoyed this. Thanks. Have a great I think this is the last week of your program, right?
There's one more week, but
One more week.
But next week all the students are going to be giving their presentation, so we don't have any guest lecture.
Sweet, awesome, that'll be great. All right.
Yeah. So thanks. Yeah. So are there any questions now before Michelle leaves? Before we head over to the next portion of the class.
All right. Okay. Thanks, everyone.
Okay, thanks. Bye-bye.
Bye.
Thanks. Bye.